this chapter, we will be looking at various types of functions. In this lesson, we will be looking at the characteristics of the graphs of rational expressions.
So here we go. Rational functions are functions of the form, okay, f of x is equal to p of x divided by q of x. So we've got polynomial divided by polynomial. Okay, and it's just like it says here, p of x and q of x are both polynomials. And with the one notable little exception here, we can't allow the denominator to become equal to 0. Okay, let's just zoom in. Whoops, zoom in. We can't allow the denominator to become equal to 0 because then that leads to an undefined, okay, an undefined expression in there. Now, turns out when that occurs, there's some interpretation here. It affects the graph in a way, if you will, and that's what we're going to look at right now, quite specifically in this chapter. So here we go. Just as an example here, we're going to take a look at some examples of rational functions here. One is 1 over x, okay, 3 over x plus 2. Okay, as long as you've got x basically in the denominator here, we call it a rational function, because functions are defined in terms of where the variable shows up. Now, these guys right here, this one, even this guy right here, they're all fundamentally different than this one right here. Notice what's going on with this one. There is a -3 out the back end here. So there's your rational, and then we're going to subtract -3 from it. Now think about that from the chapter on transformations. And ultimately that's what we're going to do. We're going to talk about the transformations on this thing. But what this is doing is taking our rational here and dropping it 3 units down. So this one's a little different than the other ones here, because the other ones don't have that. But yeah, polynomial over polynomial. And each one of these things is going to have its own little restriction here, okay? Remember here, I can't let x go to 0. Can't let that happen. Now, this does not mean I can't let x equal to 0. I can't let the denominator go to 0. So if x is 0, that's just great. 0 plus 2 is 2. 3 over 2 is 3 over 2. Awesome. But I can't let x be -2, because -2 plus 2 is 0. Okay, that's no good. So x here can't be equal to -2. Okay? This one over here, again, it's the denominator that's the issue here. I can't let the denominator go to 0. X by itself could go to 0, because that would just be 6 over -2, and that's fine. But if x is 2, then you get divided by 0 in there, and I can't let that happen, so I'm not allowed to let x equal to 2 here. Now hopefully at this point you're starting to see the pattern here. In this case, I can't let x equal 3. Because if x is equal to 3, the denominator goes to 0. Can't let that happen. And here, it's x cannot be allowed to be equal to -3. Okay, so those are the restrictions here. I just want you to be aware of that. Now, I'm going to take a quick look. I'll zoom out a little bit here. We're going to take a look at the most basic rational function we can come up with. Y equals 1 over x. And this is what its graph looks like. Okay, if you really wanted to throw a name at that, okay, because everything's got to have a name here, we call this a hyperbola. Now, not all of the rational functions we're going to look at here are going to be hyperbolae, but this particular one would be considered a hyperbola. Now we're going to take a look at the characteristics of it. Okay, so kind of move this over a little bit. Okay, it's got a non-permissible value here, right? We cannot allow x to be equal to 0. So now what happens near the non-permissible value here? Okay, well, as you approach as you approach 0, the absolute value of y becomes very large. When x approaches 0, when we get closer and closer and closer to 0 from the left-hand side, our x value here, our denominator, gets closer and closer and closer to 0. But if you're approaching it from the left, all of those values are negative. So you're going to have 1 over -1/2, 1 over -1/10, 1 over -1,000th, and so on. And as x gets smaller, the 1 over causes it to reciprocate, and that produces a larger and larger value. So as we get really, really, really close to 0 here, that reciprocal creates very, very, very large values, but all in the negative direction. 0 doesn't exist. I cannot put 0 into that. It is undefined. But immediately afterwards, if you approach 0 from the right-hand side, all of these values are positive. It's doing the exact same thing. Every time you reciprocate a really, really small x value, like really, really close to 0, the reciprocal goes really, really large. But in this case, they're all going to be positive. So what happens here is this gaping wound really in this graph here. There's this huge hole, because this drops down to -infinity. This pops up to +infinity. There's a hole here, a place where the graph becomes discontinuous, if you will, okay? And in fact, what we would say here if you want to give it some vocabulary, we would say that at x equals 0, there is an essential discontinuity. Now, we're going to have a name for that. Now, obviously, you've probably looked at this before. It's called a vertical asymptote. But we call it an essential discontinuity because you're stuck with it. Okay? I can't do anything about it. It's in the denominator. It's stuck in the denominator. It's leading to this undefined value here. Boom, there it is. Now, my end behavior. As the absolute value of x becomes really large, now what we mean by that is as you go really, really far in the positive direction or really, really far in the negative direction, so we're going quite a ways from the origin, to the right and to the left, okay? This is talking about moving this way and this way horizontal. Okay, what happens to the graph here is that the y gets closer and closer to 0. That actually should make a lot of sense because as x gets really, really large, the overall value of the fraction is going to get very small. Just like when x got really, really small, when it got close to 0, the reciprocal got really, really large. And that means away from the y-axis, away from the x-axis. Okay, either direction, really, really large values going away from the x-axis here. As x gets really large, the opposite happens and it gets really, really small, closer and closer to the x-axis. Okay? So my domain here is going to be that x cannot be equal to 0. My range is going to be that y can't equal 0. Now that might not be obvious here, but just think about it. Okay, when we're looking at 1 over x, okay, let's just think about that. Is there any value that I can plug in for x that will cause this thing to equal 0? No. No, it doesn't. I mean, just think about it here. 1 over x is equal to 0. Okay, let's multiply both sides by x to get rid of the denominator here. Well, x times 0 is 0, and 1 doesn't equal 0. Okay, you could think about reciprocating it, but then you end up with 1 over 0, and again, that's undefined. So like it just there's nothing I can do here. There's no value of x that makes that true. So y can't equal 0, which means it's got a vertical asymptote here at x equals 0. Okay, that's my y-axis, x equals 0, and it's going to have a horizontal asymptote at y equals 0. Okay, it never actually gets to that line there. It approaches it, gets awful close to it, gets ridiculously close to it, but never actually becomes the x-axis there. So those are asymptotes. Now we're going to talk a little bit more about asymptotes in just a second.
In this section, we will be looking at how to identify the vertical asymptotes of rational functions.
Okay, so when we talk about vertical asymptotes of the rational functions, we're talking about a very specific type of non-permissible, okay? And it leads to what I've said before, or called before, an essential discontinuity. Now, what's happening here, this is a special type of non-permissible value, and the description is right here. When a rational function, where you got p of x and q of x, when they have no common factor, in other words, I can't cancel it out here. What you're stuck with here is a factor in the denominator that can go to 0, that can create a non-permissible, but it has no corresponding equivalent factor in the numerator. You are stuck with it. You can't cancel it out. It's there for good. It's essential. And what that does is that corresponds to a vertical asymptote. And there's my vertical asymptote is going to be x equals the non-permissible value. Okay, and a rational function can have several vertical asymptotes, but as soon as you've got more than one here, then it's no longer going to be called a hyperbola. Okay, the hyperbolic shape here really just has it looks like this. You've got the branch here. If you throw other little holes in there, it's no longer a hyperbola. But anyway, so here we go. I've got an example here, y equals 1 over x plus 2. I've got that factor, binomial factor in the denominator. There's no corresponding factor in the numerator to cancel with it. I mean, even if I did have one, as long as it wasn't identical to this is going to lead to an asymptote. Okay, the non-permissible value is -2. That is a discontinuity in the graph, and it's essential because I'm stuck with it. The vertical asymptote is therefore at x equals -2. For this next one, I've got two binomials in the denominator. Okay, x plus 3, x minus 1. Again, there's no corresponding equivalent factors in the numerator that I could cancel it with, so those are essential. I'm stuck with them. They're going to create asymptotes. So my domain is going to be x can't equal -3 and +1, which means I'm going to have vertical asymptotes that are x equals to -3 and +1. Now, remember what's going on here, or you should see the difference between these two. When I'm talking about the domain, I'm talking about the function, the actual function I'm working with, and x in this function here, zoom in, x cannot be equal to -3 or -1 in this, +1 in this function. But when I'm asking about the vertical asymptotes, x can be that because I'm talking about something different than the function. Okay, I'm talking about a line, okay, a vertical line that the graph approaches. Okay, and so that in this case it is x equals -3, x equals +1.
In this section, we will be looking at how to identify the horizontal asymptotes of rational functions.
Okay, now let's take a few minutes to talk about the horizontal asymptote. So a horizontal asymptote is a horizontal line that the graph approaches as x gets really, really large in either the positive direction or the negative direction. Basically, the further away you get from the origin, horizontally here. Now, a rational function can have several vertical asymptotes, and we've already seen an example of an expression that had 2 of them. But it can have at most 1 horizontal asymptote. You are going to see examples of functions later on in a later math course where you can have more than 1. But for right now in this course, no, we're going to restrict ourselves to functions that only have the 1. Now, the graph of a function can't cross a vertical asymptote. It does not cross a vertical asymptote. No, because it's an undefined. Okay, the graph cannot pass through a point where it is undefined. But it could cross a horizontal asymptote. Okay. Now, for the most part, though, ours won't. Okay, we're not going to be looking at functions where that actually occurs, and you see as this discussion kind of develops here that idea pans out here, that we're not looking for graphs that do that. Okay, typically you're going to get a line here and it's going to drop down and just approach it like that or go the other way. However, it is possible for a function to, for example, cross and then approach a horizontal asymptote. It could even do this, where it crosses it an infinite number of times. But what happens is it gets closer and closer and closer to that line as we go further on here. But this is really the sort of thing that we're going to be looking at mostly in this course. Now, how do we go about looking at this here? Well, one way to do it is to just look at the basic structure of a rational function here, and a very basic rational function. So think about this. Compare this to y equals 1 over x. Okay, it's been horizontally translated and vertically stretched, and then vertically translated. Now, when you look at these basic transformations of the basic rational function, so I'm not talking about throwing an x squared, x cubed in there. We're just talking about a very basic function right now. That vertical stretch isn't going to change the horizontal asymptote because the horizontal stretch leaves the x-axis invariant. A translation certainly won't do it. So the only thing that's going to change it will be the vertical translation. So however you vertically translate it, because it starts at 0, if you move it 1 up, the horizontal asymptote is now at y equals 1. If you move it, for example, 2 down, it's now at y equals -2. And so that's why the horizontal asymptote will be y equals k. Okay, so now that's one way of looking for the horizontal asymptote, is to identify that vertical translation. But when you're seeing just some very basic transformations of the basic rational function, they won't always be written like that, though. Okay, sometimes they will be more complicated, polynomial over polynomial. So what do you do in that case? Well, if it's written in the form where you got p of x over q of x, and now here we go. The degree of the numerator is equal to the degree of the denominator. Okay? Then the numerical coefficients of the highest degrees then you simply divide the numerical coefficients of the highest degrees by each other, and that's the horizontal asymptote. So in other words, if you've got something like this, if you've got y is equal to, I don't know, let's say ax to the m plus ... over bx to the n plus ... Okay? Then my horizontal asymptote will be, if m and n, let's zoom in on that. So I'm assuming m is the largest degree in the numerator, n is the largest degree in the denominator. If those two are equal, so if I've got ax cubed over bx cubed, then my horizontal asymptote is going to be a over b. It's going to be the ratio of those two terms. Now notice, I don't even care what else comes after that. It makes absolutely no difference. Because this right here is the largest degree term. This is what is going to affect what this graph looks like as we go further and further away here. Whatever else you add here, doesn't really matter what the degree is. If the degree is less than m, it's doing peanuts. Think about it, like make x equal to 1 billion. If you make 1 billion cubed, that's like unbelievably large. 1 billion squared is nowhere near that. 1 billion billions is way bigger than 1 billion billions. So the rest of these numbers here become completely irrelevant. Essentially what happens here is if these are the same degree, they cancel out and you're just left with that right there. So that's one way of going about it here. Now, if the degree of the numerator is less than the degree of the denominator, so let's say we'll go back to this expression right here. So you've got x squared over x cubed. Well, this thing kind of reduces down to this. You're going to get ax, let's say, squared over bx cubed. Well, remember all the other terms, here I'll zoom in again on that. All the other terms behind these guys are irrelevant. Particularly when you're talking about really, really large values of x. Everything else is just, it's so tiny in comparison it doesn't matter. So nothing else here matters. When you got x squared over x cubed, that is really going to kind of boil down to a over bx. I'm kind of canceling those values there. Remember, it's because I can ignore everything else. I'm just focusing on the highest degree terms. And now if you let x get really, really big, if the denominator gets big, the whole thing gets really, really small. And by small, I mean it's going to approach 0. Oops, sorry, you can't see that. And so that's why we say that the horizontal asymptote is 0. If the degree of the numerator is less than the degree of the denominator is getting big much faster, then the asymptote is 0, y equals 0. On the other hand, if you've got, for example, ax cubed plus, and I don't care what comes after that, over bx squared plus, I don't care what happens after that, all that stuff is irrelevant. It's only the largest degree terms that matter. Then this is really going to become the same as ax over b. I can cancel out the shared values of x. And now, as x gets large, what does this do? Well, it gets large, right? X is now in the numerator. The larger the numerator gets, the larger the fraction gets. So what happens is this is actually going to take off to infinity here, okay? Or positive or negative infinity, depending on which direction you're going, whether you're going it even depends on A and B, whether you're going to positive or negative infinity. But the whole thing here is that there is no horizontal asymptote. There is no number that the function gets closer and closer to. It just gets bigger and bigger and bigger in either the positive or the negative directions. So no horizontal asymptote. So those are your rules here. Okay? So it's either going to be, here we'll zoom in. It's either going to look like this, where it's just a transformation of your basic rational function, in which case you're going to look for the vertical translation. Or, if you've got poly over poly and the degrees are the same, then it's just the ratio of those first two numbers. Don't care what else happens in there, it's just those first two numbers. If you've got a smaller degree in the numerator and a larger degree in the denominator, then when they cancel, okay, when everything else disappears and you're just left with the important stuff, that x in the denominator is going to force this whole thing to go to 0. And if the larger degree is in the numerator, well, that means that this whole thing is going to kind of look like this at the end, and that numerator is going to determine the direction this goes, and it's just going to get either bigger in the positive direction or bigger in the negative direction. No horizontal asymptote.
Identify any asymptotes that occur in the following functions.
So here we go. For y equals 3 over x minus 2. Okay. Now notice, for something like this, it's going to be undefined when x is equal to 0. So there's our vertical asymptote. Okay, at x is equal to 0. Now, that's what we'd call an essential discontinuity again, because I'm stuck with it. There's nothing I can do. Even if I add these two together, I'm still going to have that undefined there. Now, in terms of the horizontal asymptote, let's just take a quick look here. take a look at the function right here. This is a rational function, 1 over x, with a vertical stretch by a factor of 3. That won't change a horizontal asymptote, okay? But moving it 2 down will, and so we're going to get a horizontal asymptote here at y equals negative 2. 2 units down from where it should be at y equals 0. Now let's take a quick look at this one over here. This one here is going to be undefined when x is equal to 7. Now, not at 0. If you plug 0 into this, you're going to get negative 1 over negative 7, which is just 1/7. There's not a problem with 1/7. But if you plug 7 in, okay, you're going to get 13 over 0. Well, that is a problem. So 7 is not acceptable, so we're going to get a vertical asymptote at x is equal to 7. Now, for my horizontal asymptote, what we're going to do is we're going to compare the largest degrees here. So when we're talking about really, really big values of x, okay, -1, like if you've got 2 times a billion and you subtract 1, if you had $2 billion and you lost a loonie, would you care? No. No, not at all. If you had $1 billion and you lost $7, you wouldn't care. Those things don't really mean much. So when we compare the highest degree terms, 2x over x, the x's cancel, and we're left with y equals 2, that is your horizontal asymptote. Okay? Now come along over here. To figure out the asymptotes of these things here, actually what we need to do first is we need to factor both the numerator and denominator. And this is an idea that's going to get explored a little bit more. We're just kind of introducing it here, but you'll see what I mean here. You're going to get x, what do we got here? X minus 4, x minus 3, all over x plus 3 times x plus 3. Okay. Now, notice in the denominator we've got the same non-permissible popping out of that. Okay, that's going to be our final answer. Our vertical asymptote is going to be at that non-permissible x is equal to negative 3. Now you got to watch this. You have to factor both the numerator and denominator here, because if a factor was shared, it turns out that's not a vertical asymptote. If this was x plus 3 up here, this wouldn't be a vertical asymptote. And we're going to talk about that in a little bit. But something you got to watch out for here. Now, the horizontal asymptote, once again, because of we got polynomial over polynomial, we can ignore all the lower degree terms. We are just interested in the highest degree terms. That's it. Because when we got really large values of x, these are the terms that are going to dominate what these things look like. So you can ignore everything else and we get x squared over x squared. Well, that's just 1. So we're going to get a horizontal asymptote at y equals 1. Okay, let's drop down. Next one here, we got 3x plus 2 over x squared minus 9. Again, I need to factor this. Can't really factor the numerator, so I'm just going to leave it as 3x plus 2. But the denominator can be factored. X plus 3, x minus 3. It's a difference of squares. So now I'm going to have 2 non-permissible values here at positive 3 and negative 3. So that means I'm going to have 2 vertical asymptotes at positive 3 and negative 3. Okay. Now, when I compare the highest degree terms here, in the numerator, the dominant term is 3x, the dominant term in the denominator is x squared. Okay, now if I cancel out an x there, essentially this is going to become the same as 3 over x. And if you let x get really, really large, this tends towards 0, gets smaller and smaller and smaller. So we're going to get a horizontal asymptote at y equals 0. And again, the other way of arguing that is if you memorize the rule, the denominator has a degree higher than the numerator, it's going to go to 0. Okay, because the denominator is going to grow that much faster than the numerator. All right, here we go. Let's keep going here. We're going to factor. Got to factor. So in the numerator, I can take out a 5, and I'll be left with x squared. Sorry, if I take out this 5, I'll be left with x squared minus 4. So this can be factored to x minus 2, x plus 2, over 2, x plus 3. Okay, again, there's nothing common between the numerator and denominator, which is good. Good, I like that. So what I'm seeing here, whatever's undefined, is going to be a vertical asymptote. And I see this is going to be undefined at negative 3. So I'm going to have a vertical asymptote at x equals negative 3. And again, for my horizontal asymptotes, I don't care about any of those other terms. I only care about the dominant terms, the one with the highest degree. So 5x squared over 2x, that's going to be the same as 5x over 2. I can cancel out the common 2's. Again, remember, in this particular case, I'm not worried about the 20 and the 6. Doesn't matter. It's just those two that I'm comparing. But now, if you let x get large, well, that ratio gets large. It doesn't tend towards any one value. It just gets large and larger and larger. In other words, the numerator here is going to grow substantially quicker than the denominator, which means there's no horizontal asymptote. Okay? Just doesn't exist. That's fine. It's okay to have that kind of an answer. Let's take a look at this last one here. Where is this thing undefined? Nowhere. There's no x in the denominator. The x is 7. Well, 7 doesn't lead to an undefined value here, so there's no vertical asymptote. There's no vertical asymptote. What's the degree of the numerator? The degree is 1. What's the degree of the denominator? It's 0. Okay? 7 is the dominant term. If you compare dominant terms to dominant term here, well, the numerator is going to grow, the denominator doesn't. So as x gets large, this whole thing is going to get large. Turns out, same thing here. There is no horizontal asymptote. Now, that actually makes a whole lot of sense for this particular equation here, because when you take a good look at it here, what is this? Well, if you distribute the 7 to both of those terms, you're going to get x over 7 plus 6 over 7. Well, this is just a line. Okay, this is just an oblique line. It's off at an angle here. It has no horizontal or vertical asymptotes, because that's exactly what it is. Just a line.
And now for a quick summary before we proceed with applying the information you've just learned.
So now, just for a couple of moments here, we're just going to summarize where we're at here. When you've got a rational expression written in this form right here, okay, notice that the a, the constant at the top here, is going to be the vertical stretch. Really, because this can be written like this. You could think of it as a times 1 over x minus h, and then with the plus k right there, where the function is this rational expression. Okay, so we got 1 over, because x is in the denominator, that's what makes it rational here. So a could be factored out or moved out to the front here, so it's in the position of a vertical stretch. H is going to be that horizontal shift, okay, and as a result, okay, because this thing has a vertical asymptote that would normally be on x equals 0, whatever the shift is, that is going to translate directly into our vertical asymptote. And then k right here is our vertical shift, and as a result, it ends up being also our horizontal asymptote. I was going to say vertical asymptote, but that's incorrect. That's horizontal asymptote, because the rational function all on its own is going to have a horizontal asymptote at y equals 0, and moving it k units in whichever direction we choose to go here is going to move that asymptote in k units, and so that's going to be our asymptote. So there's a quick summary of the expression in this form. Now let's just flip the page here and take a look at what we got here. This is the other way of writing your rational expression, where you've got polynomial over polynomial, where everything is kind of contained within this rational expression right here. And I kind of like the way this has been broken up here, because there's like 4 different things you're really going to be looking at, and this does just a marvelous job of identifying that. Okay, the x-intercept occurs when the y-coordinate is equal to 0, okay? When the y-coordinate is equal to 0. Now, the only part that will make a rational expression equal to 0 is when the numerator equals 0. If the denominator goes to 0, it's undefined. Okay, and you gotta remember that. It's very tempting to want to make numerator and denominator 0 for the x-intercept, but it doesn't work like that. It's just the numerator that makes it 0. 0 over whatever is 0. So that means, based on this expression right here, that my x-intercept would be, on this one right here, negative b over a. The vertical asymptote comes from the denominator going to 0, okay, in which case the vertical asymptote, and again, it doesn't matter what the numerator is doing, the vertical asymptote here is going to be d over c. Now, the horizontal asymptote, in this particular case here, if you've got similar degrees, and we've talked about this, similar degrees, the horizontal asymptote is going to be the ratio of those two leading coefficients, okay, with the highest degree terms, okay, and the y-intercept, and remember what you do for the y-intercept. For the y-intercept, you let x go to 0, and when you let x go to 0, what's going to happen here is this is going to collapse, and all you're going to be comparing are going to be the trailing coefficients, or the constants in the numerator and denominator. So you get the horizontal asymptote from the coefficients of the highest degree term. You get the y-intercept from the least degree term, the degree 0. Okay, that's a nice little bit of symmetry that this particular box here highlights in those polynomial functions, the polynomial over polynomial to get the rational. Really like that. Does that really well.
Match each of the following graphs with one of the following equations.
Okay, so when we match these things, we're just going to go through and look at the expression here. Just yank out the details that are important and compare them here. So look at this guy right here. This one's going to have a vertical asymptote at x equals positive 2, because it's going to be undefined at positive 2. So x equals positive 2 is my vertical asymptote, and notice that the degree of the numerator is less than the degree of the denominator, so its horizontal asymptote is going to be y equals 0. So now I'm looking for x equal to positive 2 as my vertical asymptote. Okay, well this isn't it, because here the vertical has the asymptote is at negative 2. This one here, it's at 0. Here we go. Here it is, positive 2. And notice that the horizontal asymptote here is 0. It looks like it's approaching 0 as we go to the left and the right here. So this one goes with I, the first one. Now let's take a look at the second equation that we've got here. In this case, this thing is going to be undefined when x equals negative 2. So that's my vertical asymptote, negative 2. Again, the degree of the numerator is 1 less than the degree of the denominator, so our horizontal asymptote is going to be 0. So we're looking for those two qualities right there. And we actually don't have to go any further than A, because I can see right here my vertical asymptote is at negative 2. It's approaching negative 2, but it's approaching that asymptote, going off to infinity, down to negative infinity. And as x gets larger, it's getting closer and closer to 0. So here we go. There's our graph right there. Whoops, I don't know why I wrote pi there. Haven't got a clue. And there's equation 2 right there. Okay, next. Okay, so this is a different form. Here, based on this, I can see that my vertical asymptote is going to be where this is undefined at x equals 0. My horizontal asymptote here should also be y equals 0, but it's been moved 2 units down. So y equals negative 2. So now I've just got to check between B and D here. Okay, vertical asymptote at 0. Okay, could be B. But in this case here, the horizontal asymptote appears to be positive 2. Down here, here's where it goes to negative 2. So this is I, number 3. And now by default, it's got to go to this one here. But let's just take a quick look at it. My vertical asymptote here is going to be x equals 0. Yeah. And my horizontal asymptote is going to move with the vertical translation, and this is 2 up, so my horizontal asymptote is going to be 2 up from 0, y equals 2. So yeah, there it is right here. Okay, good. And we've matched them all.
Complete the following table.
Okay, so here we go. Now what we're going to do is we're going to run across the columns here. Sorry, I can't believe I just said that. We're going to run across the rows here instead of going down the columns for each of these. So vertical asymptote, what we're doing is we're identifying where these things are undefined here, right? So for our first one here, this is going to be undefined when x is equal to 0. Now for a second one here, normally we'd have to factor numerator and denominator, but we don't need to do that in this case because it's already factored. So our undefined here is going to be when x is equal to 7, so that's our vertical asymptote. And over here in our last case right here, this is undefined here at x equals 2, so that's our asymptote. Our domain, which is the next thing we're going to look at here, is related to the vertical asymptote. So x can't equal 0, x can't equal 7, x can't equal positive 2. Okay, so our vertical asymptote and our domain are basically stating the same thing, just from, I guess, opposite directions here. Our horizontal asymptote. Well, look at the way this one's been written here. This is just a very basic rational expression. There's been no vertical translation. So our horizontal asymptote we would assume to be y equals 0. Here, again, we're comparing the highest degree terms. Notice that it's 2x over x. Okay, when you simplify that little relationship there, we're going to get y is equal to 2. 2 over 1 or 2. And here, without this negative 3 at the end here, again, this is just a rational expression. Its horizontal asymptote would be at y equals 0, okay, because the stretch in the translation won't affect that. But when you translate this 3 units down, we're going to get that y cannot equal negative 3. Now, the range. in almost exactly the same way that these two are related, the vertical asymptote, the domain, for us, the horizontal asymptote and the range are going to be the same here. So y cannot equal 0, y cannot equal 2, and then over here, whoops, sorry, I anticipated where this was going. Sorry, I anticipated where this was going. Y is equal to negative 3, and then down here the range will be y can't equal negative 3. Okay. Now that's not always true for rational expressions, the relationship between the horizontal asymptote and the range there. But for us, you can basically bank on that. In terms of what you're going to get tested on, that's a very, very safe bet. Now let's go down here to the y-intercept. Oh, sorry, x and y-intercept. Okay. Now our x-intercept is going to be where y is equal to 0. Okay. Well, there's no value of x that'll make that true, so there is no x-intercept here. Okay. The x-intercept is going to be what makes y equal 0. Well, the denominator has no say on that. The denominator will not affect that, so it's only going to be where the numerator goes to 0, and that's going to be when x is equal to 1/2. That will make y equal to 0. Okay, down here, now this is an interesting one. This is going to lead us to a little equation here. Let's go down here, we're going to solve this. So 0 will equal 6 over x minus 2 minus 3. Okay, we get a little equation here when we solve for the x-intercept, and you always do. Okay, that's always true. Solving for an x-intercept involves the creation of an equation here. Bring the 3 over, so we get positive 3 is equal to 6 over x minus 2. Notice I've got a 3 here and a 6. I can actually simplify that and make that 1 is equal to 2 over x minus 2. Now I'm going to multiply both sides by x minus 2 is equal to 2, so x is equal to 4. There's my x-intercept. X is equal to 4. I love that. Now let's go down and we're going to find the y-intercept. Now the y-intercept involves making x equal to 0. Well, if I do that, it's undefined. Okay, yeah, there's no y-intercept here. And actually, that makes perfect sense. Okay, because think about this. This graph is going to look like this. It's going to come down, down. Yeah, sure, it's had a vertical stretch by a factor of 4. But that's not going to affect the asymptotes here, which are both on the axes. Yeah, so there's no y-intercept there. Y-intercept here, we're going to make x equal to 0. That'll get you negative 1 divided by negative 7. Okay, so y is going to equal positive 1/7. Over here, we're going to make x equal to 0. Okay, now 6 divided by negative 2, because I got to do this in terms of order of operations, so I got to do the division first. 6 divided by negative 2 is negative 3, minus 3. That's going to be negative 6. Okay, and there you go. So there's all the information that we're looking for these three rational expressions.
Write the equations of the following graphs in the form y equals a over x minus h plus k.
Okay, so we're going to come up with the equation of this rational function here. Now, notice that we're supposed to come up with the equation in this form here. I'm not going to be able to find without doing some substitution in here, okay? As a vertical stretch here, I need to know a point, and I need to plug that in order to solve for that. But h and k, I can typically get fairly easily by just looking at the graph, okay? Because I know already that the horizontal translation is going to be aligned with the vertical asymptote here. My vertical asymptote seems to be x equals 2. Now, that should have been on 0, so this thing has been moved 2 to the right here. So x minus 2 equals 0. Okay, well, they're right there. Oops, sorry, you can't see that. Right there, that's got to be the denominator of this function. That's got to be this part right here, giving me this vertical asymptote. I know right here, okay, that my horizontal asymptote, which should have been on 0, has been moved up. Okay, has been moved up 3. So in this case here, y is equal to 3. Now, up 3 is going to correspond with my k value there. So I know right here that k is going to equal 3. So where this leaves me right now is I'm at this point. I know y is equal to a, don't know that yet, over x minus 2. That's going to give me that vertical asymptote at 2, plus 3. That's going to give me the horizontal asymptote at 3. Now I'm going to pick one of these 2 points that they've highlighted. Okay, and that point looks right there. And I'm going to use the one with the smaller coordinates because I'm lazy. 1, 2. Okay, So x is 1, y is 2 here. So I'll come to this expression right here where y is equal to 2, x was equal to 1, and I don't know why I put negative 1 there. 1 minus 2 plus 3. Okay, first thing I'm going to do is I'm going to bring that 3 over. Okay, so I'm going to subtract 3 from both sides. I'm going to get negative 1 is equal to a over. Now we'll evaluate the denominator, which is going to end up being negative 1. Multiply across here. I'm going to get kind of the anticlimactic result here that a is equal to 1. So what that means is my equation really should have been 1 over x minus 2 plus 3. That's the equation that we're looking for this rational function. So in this case, very similar to the previous one that we did here, we're looking for the equation in the same form. So I'm going to look at what my asymptotes are and get the transformations from there. So right here I can see that my vertical asymptote appears to be where x is equal to negative 2. Bring that over and I get x plus 2 equals 0. Well, I can't let that happen because that's where it's, where it's undefined. That right there ends up being my denominator. Okay, x plus 2. Good. So I got that part of it done. Now I'm going to take a quick look here. Notice my horizontal asymptote appears to have been moved down to negative 4. So y equals negative 4. That means k is equal to negative 4. That vertical translation, that's what's moving that horizontal asymptote. That becomes my k value. Perfect. So now I can come over here and I can write out my expression, or my equation here. Y is equal to a, still don't know what that is, over x plus 2 minus 4. Now I'm going to pick one of the 2 points that they've highlighted here, but again, I'm super lazy, so I'm going to use the one with the smallest coordinates here. And this point right here looks to be negative 1 comma negative 1. Well, I like that. So I'm going to plug that in. So negative 1 for y, a over negative 1 plus 2 minus 4. First thing I'm going to do is bring this second term over. I'm looking for the a. I want to get rid of the term that doesn't have the a in it. So I'm going to add 4 to both sides, and that'll get me 3 over here. And then negative 1 plus 2 is positive 1. So a is equal to 3. So now I can write my expression y is equal to 3 over x plus 2 minus 4. Good. That's the equation that we're looking for. That's the equation of that particular rational function.
Now we will take a couple of moments to talk about how to solve rational equations graphically.
Okay, before we get into actually solving some of these equations in a bit here, we're going to talk about solving equations graphically, just a couple of things that you need to be aware of here. There are 2 ways that you can go about doing this. Okay, one way is to put everything, bring everything in that equation over to one side so that it's equal to 0. So a good example is this one down here. Everything has been brought to one side so it's equal to 0. Now think about this. If I'm going to graph this, what I want to do is I'm going to make y equal to this right here to graph it. But in actuality, the y isn't there, it's a 0. Now, what am I looking for when I replace y with 0? Well, I'm looking for x-intercepts. I'm looking for where the graph hits the x-axis here. So that's one way to do it. Okay? Plug this all in, bring everything over to one side, plug it in, look for the x-intercepts. Another way of doing it, though, might be like with this one right here. What we'll do here is we'll split this up into 2 separate functions. Okay? We'll graph this function, y equals this function. We'll graph this function, y equals this function. We're looking for where the 2 functions are the same, where they're equal to each other. That's going to be a point of intersection. Okay, and then we'll grab the x-coordinate out of that, and that will make this side of the equation equal to this side. It doesn't really matter which method you use. You kind of got to pick and choose whatever method kind of makes the most sense to you. However, you need to be aware that both of these are options, because I have seen them test or throw questions out there where what you're being tested on is how comfortable you are with both of those methods, okay? And graphing bits of information and putting them together in different ways to get solutions, okay? So you need to be aware of both regardless of whether you favor one or the other. So we're going to jump right into solving here in just a second.
Solve the following rational equations graphically. If necessary, round the answer to the nearest tenth. X plus 6 divided by x plus 2 minus 5 equals 0.
Okay, so we're going to jump right into solving this one, and we're going to graph this one and look for the x-intercepts here. So pull up my calculator. Now I should state here while I'm plugging this in, so I'm going to move this over here so I can see the expression as well. So y equals x plus 6 divided by x plus 2. Whoops. Got to make sure you put parentheses around the denominator. If you don't, then you're not actually dividing by what you've entered, what you think you're dividing by. If I didn't put the parentheses there, I would be dividing by x and then adding 2 to the whole expression, minus 5. And I'm looking for where this is going to equal to 0. Now I should mention here, okay, that if you solve something graphically, you will not be solving, you will not be able to find extraneous roots. Sometimes you get asked for extraneous roots. Those are it's only possible to bump into those when you solve things algebraically. So just be aware of that. For right now, we're just looking at solving these things graphically. So I'm going to press zoom number 6 because I don't know what my window settings are. Let the calculator deal with it. Okay, so there you go here. Now, I'm a little concerned. I know that I'm going to have an x-intercept here. Sorry, a vertical asymptote here at -2. I can tell that from my equation here. I know that I'm going to get a vertical asymptote here. X can't equal -2. I am a little concerned about what's going on over here. I can't see it here. So what I'm going to do is go to my table settings, and I'm going to go down here, and okay, take a quick look. When I go into my negatives here, into the negative x coordinates, at -3 I've got -14. Well, that's below my screen. Then as I go further back here, it goes up to -12, and then it starts to drop down again. So what that means is down here, the graph has come up, and then it's moving away from the x-axis here. If I want, I can go into my window and maybe drop my my y-min to, let's say, -20. There's that bottom part there. Okay, I feel much better now that those are the only two solutions that I'm going to get here. So now to find those, I'll press second trace, which takes me into this calc menu, and I'm going to look for the 0. Okay, the 0 of the function, where the y coordinate is equal to 0. Now I move my cursor, first of all, just to the left. Okay, don't use the up and down arrows, just use the left and right arrows. I move it to the left of my 0, press enter. Move my cursor to the right of that 0, press enter. I get these two little triangles up here. My x-intercept should be between those two. Press enter to get past the guess. And I'm getting 1, 0 at -1. So one of my answers here is x equals -1. Now I'll do this again. I press second trace. Press number 2 to use my 0 function. Then I come over here. Okay, right now I am to the left of that 0, so I press enter, puts a little triangle up there. Move to the right, press enter, puts a little triangle there. And again, as long as my x-intercept is between those two, the calculator will find it. Press enter past the guess, and I get 0. X is equal to 0. Oh, sorry, x is equal to 4. I can't believe I said y is equal to 0. X is equal to 4. Now I'm going to show you something here really quickly because you need to be aware of this. I'm going to go back in and I'm going to solve this. What if I didn't do it like that? What if I didn't move the cursor over? Because you're going to need to know how to do this. You're going to need to troubleshoot on the exam. If I press enter here, and then I don't go quite far enough. So now what happens here is my x-intercept is not in between those two. When I press enter, the calculator gives me this error, no sign change. Okay? So you need to know how to respond to this. If you're doing a major exam like the diploma, the people in there supervising, if you raise your hand and say, hey, there's something wrong with my calculator, I'm getting this error here, you need to understand that those people may not be able to help you. So you got to be able to troubleshoot on your own here. This means, no sign change, means that you didn't put that 0 in between those two sides there, those two lines there. Anyway, I hope that helps you solve that. We're going to now solve the other two here.
2x divided by x plus 3 plus x divided by x minus 3 equals 18 divided by x squared minus 9.
Okay, so for this question right here, what we're going to do here is we're going to split this up and we're going to graph both sides. So you've seen both methods here. We're going to graph the left side and then the right side here. Okay, so pull up my calculator here. And what I'll graph here is on the left-hand side here, 2x, whoops, why did I do that? 2 x, and I'm putting parentheses around that because that's my entire numerator. It really doesn't matter here, but it does matter that I put the parentheses around my denominator. So I'm going to do both. Plus x. Now there is only one factor even in the numerator, so I don't even have to put parentheses around that. But again, I do need to put them around the denominator so that the calculator understands this whole thing is the denominator. Next, I'll put down in the next function right here, 18 divided by, again, parentheses, x squared minus 9, close parentheses here. I'll graph this. I don't know what my window settings are, so I'm going to press zoom 6. And I like the simultaneous graph so I can see both of those. Awesome. Now, it looks to me like we've got a well, here I've got the two vertical asymptotes here. They're both approaching -3 and +3 here. So to find points of intersection, we're going to press second trace. Okay, we're going to go down to number 5 here, intersect. Now, I'll tell you what, we're going to come over here first. We're going to come past, we're going to come past the asymptote. What I know is the asymptote here. I'll press enter, enter. Now, what that has done is that's chosen the first curve, the second curve. I'm going to press enter again to see what happens here. Oh, sorry, I'm going to press enter past the guess. No sign change. Okay, what that means is to the left of that vertical asymptote, these guys never cross. So now I'm going to go back into that menu, choose my intersect again, come back over here. Now it sort of looks to me like there's a point of intersection around here. And then because of some symmetry, I'm going to get one here too. So enter, enter for the second curve, enter to get past the guess. It thinks, okay, and I'm getting a point of intersection at -2, -3.6. So over here, I'll write down -2, -3.6. Now I'm going to talk about this in just a second here. Let's keep going. Second trace, intersect. I'm going to move that cursor over because it looks to me like there's something going on over here. Maybe there isn't, but maybe there is. Press enter to get to the second curve, enter, enter past the guess. And it jumps me back to -2, 3.6. Now, so it doesn't look like there was a point of intersection over here. So I'm going to come over here. Actually, I'm going to just check this one more time because maybe there's something even a little deeper down here. Now, I don't think there is, but I'm going to try here. 1, 2, 3. And it keeps bumping me back to there. Good. Now, I'm going to check intersect. I'm going to check on the far side of this other asymptote here. So I'm going to go past +3, x equals +3, come down here. Let's see if these guys intersect over here. First, second, third, go past the guess. Oh, and it jumped me over here. I'm really surprised that it jumped over that asymptote. That's really strange. I didn't anticipate that. So it looks like we're getting only one point of intersection here, the point -2, -3.6. Okay, so nothing else here. Now, what we're going to do here is to interpret this, we're going to say that x is equal to -2 because when I ask you to solve this, I'm asking for the x value. There you go.
3x minus 1 divided by x plus 4 plus 3 equals 6 divided by x minus 4.
Okay, now for this one right here, again, we're going to solve this one graphically. What I'm going to do is I'm going to bring everything over to one side. Okay, that is my personal preferred method of doing this. So I've done A and B. I did the two different methods here. Now I'm going to show you the one that I prefer here. I'm going to make this 3x minus 1 over x plus 4 plus 3. I'm going to subtract 6 over x minus 4 and let that equal 0. So now I'm going to enter this in. Okay, so here's the calculator, y equals, so in parentheses 3x minus 1, and I really do need the parentheses here because there are two terms in the numerator, and I need to make sure that the calculator understands that. And there are two terms in the denominator, and I need to make sure the calculator understands that. So I have to put parentheses around all of that. Plus 3 minus 6. In this case, there's only the one factor even in the numerator, so I don't need to put that in parentheses, divided by, but the denominator has the two terms, so x minus 4 in parentheses here. Okay, good. Now, one of the reasons why I like using this particular method here is now I don't know what my window settings are, I haven't got a clue. I'm going to press zoom number 6. But the thing is, what I know is what I'm looking for. And I am only looking for x-intercepts. Now, based on what I'm seeing right here, I'm a little curious as to maybe what's going on over here. I got these two x-intercepts right there. That looks really good here. I know from the equation, go back over here, I'm going to get two vertical asymptotes at -4 and +4. Okay, well, I'm kind of seeing that. I'm seeing a vertical asymptote here. I'm seeing one here. I'm not quite sure whether this is dropping down. It looks to me like there's a horizontal asymptote here. So I'm going to press Window. I'm going to make my x-min, let's say -50, just for fun. Okay, that does appear to be approaching a horizontal asymptote here. At least benefit of the doubt here. We're not in the, we're not in the market here of producing questions that are ridiculously complicated. There is no answer that's going to be out here in the negative millions or whatever. So we can rest pretty confident, be pretty confident that those are my two answers. So trace 0. Kind of regretting moving that over there, but anyway, here we go. So to the left of that x-intercept, to the right of that x-intercept, press enter. And I'm getting -2.1. So whoops, you can't see that. X equals -2.1. And I know I'm getting another one here, so let's keep going. Second, trace 0. Keep going, keep going. It's got to pop back up again. There it is. Enter. Go to the right, press enter. And we get 5.3. So my other answer here is 5.3. And so those are the solutions that we're looking for to this equation. Again, I like this one a little bit better because all I'm doing is looking for x-intercepts. I know, for example, that there is no solution occurring above or below the graph. I don't have to expand my window settings vertically to see the solution here. I know they're going to be somewhere along that x-axis.